50 watts per meter Kelvin, which is the thermal conductivity. Please note I made a jump here. This equation, this is the heat diffusion equation for 1D steady state, okay, which we had just written down and I erased it because I'm assuming you have taken it down too. All I need to do is differentiate twice. So this is going to be minus 4000, okay, because if I differentiate it once, it's minus 4000 times x. Differentiate it one more time, it's minus 4000. I'm not going to spend time on showing differentiations. That's my promise to you, okay? Negative sign cancels off on both sides, so this implies that I have positive heat generation because I started off with positive heat generation to begin with when I wrote this equation. We had assumed Q dot greater than 0. We are validated by the answer that we obtained. So solve for Q dot. This is 200 kilowatts per meter cube. Volumetric energy generation is energy generated per unit volume, or rate of energy generated per unit volume, so watts per meter cube. Okay, so this is positive. Draw the temperature profile. Watch this. X is equal to 0 is the left hand side. I'm going to say x is equal to some thickness T is the right hand side. The thickness is given to you as 50 millimeters or something like that. Don't really care about it. At x is equal to 0, I calculate the slope dt by dx at x is equal to 0 tells me the slope. Okay, so what is the slope here? Dt by dx at x is equal to 0 is minus 4000 times 0, the first derivative of the temperature, multiplied by whatever quantity x there is. X is 0, so this is 0. Dt by dx at x is equal to t. Minus 4000 times the thickness T is less than 0. I'm not going to calculate any of these things, and you don't need to either. What am I doing here? I'm calculating the slopes at x is equal to 0 and at x is equal to t. At x is equal to 0, my slope is 0, so for the temperature profile, I'm going to start off with a slope that is at that point horizontal. Does this make sense to everybody? 0 slope. Then at x is equal to t, my slope is negative, which means that I'm going downhill. So at this point, I'm just going to draw a line this way. And so the direction of heat transfer, it is quite easy to understand by just substituting x is equal to 0, temperature at the left hand side is 200 degrees Celsius. X is equal to 50 millimeters, temperature at the right hand side is 195 degrees Celsius. It is going to go from left to right, and the profile of the temperature distribution is going to be parabolic, and this is for Q dot greater than 0. And it is really important to understand how we obtain this. Once again, I have 2 more minutes left. Once again, temperature at this side is 200 degrees Celsius. How did I get that? Just by substituting S is equal to 0 in the temperature profile that is given to me. No big deal. Temperature at the right hand side is 195, which I also obtained by substituting x is equal to 50 millimeters in the temperature profile equation. So I obviously know the direction of heat transfer is from left to right, and I have to draw the temperature profile, which tells me exactly what I need to know. At each and every point, starting from a zero slope, which means that this is an adiabatic boundary, there is no energy transfer taking place at the left side of the wall. But as I start going from the left to the right, my temperature profile says that I am descending, and this completely makes sense because the direction of heat transfer is in the direction of the negative temperature gradient. So at each and every point, if I draw the slope, I am slowly going downhill at a constant rate, or at a linear rate. I'm sorry, the slope is not constant, the slope is linear here. First derivative is linear here. Okay? So all of these things are really important to understand. We're going to spend a lot of time just looking only at profiles, no numbers, no equations.